chemistry students. In this video lesson, we are looking at standard SE1F. We are actually introducing periodic trends. Trends are patterns that you can find on the periodic table. Hopefully by the end of the lesson, you'll at least have an idea of what the trends are and the specific patterns for each of the trends, as well as those that you can actually read directly from your periodics table. Mouse was not in the right place. So our first official law for chemistry, the periodic law. Periodic law basically says that if we put the elements in order by atomic number, you're going to have a repetition in the physical and chemical properties. So the properties of the elements repeat over and over again only when they're put in order by atomic number. Now, because of this periodic law, we see a repeatable pattern in not just the atomic number, the atomic mass, but we also see it in their nuclear charge. We see it in the phases of the elements that are in each of the groups. We also see it in these other trends that are going to be brand new to you. So ionization energy, electronegativity, metallic nature, ionic radius, and atomic radius. Those patterns repeat predictably on your periodic table, and we can use this knowledge to predict how elements will react, as well as identify an unknown element based on how it responds in chemical and physical processes. So I like to start with what we can see on our periodic table. The one that you're given in class, of course, was, printed, so it's not all pretty color-coded, but if you look at our electronic one in our Google Classroom, it is color-coded for a reason. And that is so that you can see those states of matter. You can easily look at our periodic table, both the one electronic and the physical one in the classroom, and you can see that all of these red elements, they're all indicating that the thing is a gas. So notice that most of our gases are found on the right side of the table. Our blue indicates that it is a liquid. We only have two blues, mercury and bromine. The black, that is your most common color for your symbols, and black indicates that it is a solid. And because I couldn't do outline letters on my online stuff, I chose green for our man-made. So the one in the classroom has a slightly different color for the man-made ones, but on our virtual ones, green are those man-made elements, and these are just elements that don't exist in nature. They only exist in a lab. Scientists actually have to create them. I can't spell man-made. So, anywho, our green elements are man-made. So, other information that we can get directly from the periodic table. Of course, your atomic mass. Remember, on our periodic tables, that atomic mass is written immediately below the atomic name, the atom's name. But in terms of the trend, if I look at it, I can see fairly easily that as I go across the periodic table, that those atomic masses increase. So mass increases across. And we also see that same overall pattern increasing down. So general trend, that one I can get from the table. Yeah, there's a couple times where there's a few exceptions, but trends is all about big pictures. Same thing with nuclear charge. Remember, the nuclear charge is just based on your number of protons. And your number of protons equals your atomic number. So my atomic numbers, because periodic law says put them in order by atomic number, my atomic number also increases across and increases down. So these two things have the exact same trend. Electronegativity, we will talk a little bit more about in a second, but I do want to point out that there is a number on our periodic table that has been there the whole time that we haven't really used. And if you look at your key, which isn't shown on the screen, it's this little bottom right-hand corner number. So you can actually get that exactly from the periodic table. You can see the big trends. Last but definitely not least, your electrons, valence electrons. Remember that you were able to get them from the group numbers. So I know it's not explicitly black and white on the periodic table, but that last digit of the group's number gives you the number of valence electrons for the elements in that group. So group 17, all of those elements have 7 valence electrons, for example. So a couple of things you can read right from the table. Another thing that you can infer from your periodic table is metallic nature. Metallic nature just kind of gives you an idea of how metal or non-metallic an element is. If we remember that on our tables, we have this lovely bold line. The staircase is what is used to separate metals from non-metals. And with my metallic nature, you can easily see that for the most part, everything on the left of that solid bold line are metals. And everything on the right of that solid bold line are non-metals. Yes, I know hydrogen is weird. He's confused. He's on the wrong side of the table, but he's a non-metal. So overall, in terms of trend, as I go across, I go from metals to metalloids to not metals. So my metallic nature decreases as we go across. I can also see that if I go down groups, there's a pattern. Now you got to be careful and not look at the middle of the table because it's all transition metals, so it's a little less obvious. But yes, you can see this trend with group 1, and you can see it great with groups 13 through 17. Groups 13 through 16, you go from non-metals to metalloids to metals. So as we are going down a group, my metallic nature increases. We get generally more metallic. So why is this important? Well, what that means is if I'm comparing fluorine to bromine, they're both nonmetals because they're gases. They're on the right side of the table. Well, yeah, sorry, bromine is actually a liquid. But anywho, they're both nonmetals, but bromine has a little bit more metallic character than fluorine. So it has a little bit more metallic properties. It does some things that fluorine or helium won't do. So on that note, thinking about our trends, I've already mentioned these two, but make certain you get these specific trends in your notes. So nuclear charge. What do I mean by nuclear charge? I mean the charge in the nucleus. Remind yourself that that is contributed by strictly your protons. My nuclear charge and my atomic mass both have the same trend. They both increase both directions. They increase down and they increase from left to right. Remember that your mass is the sum of protons and neutrons. But overall, the general trend is they increase as you go down the group. They increase as you go across. And from across, we are in English-speaking countries, so we read from the left side of the page to the right side of the page. And so we're almost always going left to right. Oh, arrow it was kind of funky. So, metallic nature. As I mentioned earlier, metallic nature gives you an idea of how metallic elements are. And this is one that, if you remember that dividing line, you can infer that the left side of my table is metallic, the right side of my table is non-metallic. That means francium, who is not shown on this particular image, is the most metallic because we increase as we go down and we decrease as we go across. So francium is the most metallic while helium is the least metallic. So, which means by default, hydrogen's just a little bit more metallic than helium because overall my metallic nature decreases as I go across. So our next trend is atomic radius. Just simply defining what a radius is. A radius is half the measurement from, not half, but it's the measurement from the nucleus to the outer edge of electrons. So it's half the diameter, technically. But radius, we're measuring from our nucleus to that last row, last energy level of electrons, your valence electrons. So specifically on the screen, I happen to have Bohr's model for boron and for aluminum. And if we notice, we can easily see that as I go down a group, my radius is going to have no choice but to increase, because every time we go down a group, we are adding an energy level. And every time we add an energy level, radius is going to get larger. So my pattern for going down the group kind of makes sense. Now, when we go across the period, it's a little bit counterintuitive. My periodic trend is that the radius decreases from left to right. Our radius of the atom shrinks. The reason it shrinks is because every time we go one more element over, we're adding a proton. But that proton is making that nucleus a little bit stronger. It's kind of like a magnet. And it's pulling those electrons a little bit tighter. All of the electrons are still going into the same energy level. But every time I add one more proton, that nucleus gets a little bit stronger and pulls the cloud just a smidgen smaller. It's not a huge difference, but overall we see that decrease from left to right. And it's due to the pull on the electron cloud from the addition of a proton. So, ionic radius, same pattern as atomic. What is an ionic radius? Well, it's the radius of an ion. So it's an atom that has gained or lost electrons. Now, in general, follows the same big pattern. As we go down a group, radius increases. Easy peasy, because we're adding more energy levels. As we go across, the ionic radius in general decreases. And I do want to stress the whole in general, because if you look at specific ionic radii data, what you're going to see is that it gets a little bit wonky around about group 13, 14, 15. But if we look at the big picture, remember that groups 1 form a plus 1, groups 2 form a plus 2, groups 13 forms a plus 3. That means each one of their groups is losing one more electron. So group 1 loses an electron from its cloud. Well, that means the cloud's going to get a little bit smaller because the nucleus is going to be able to pull a little bit more. If that element loses 2 electrons, it's going to shrink even more. And if we lose 3, it's even smaller, because every time we lose some electrons, the cloud is going to shrink. But when we look on the non-metal side, we see that non-metals form those positive charges. Not positive charges, bad misreadings. They form negative charges, which means they are gaining. So I was thinking positive. It's positive to give. It is negative to steal. We're going out and we're stealing some electrons. And they have the predictable pattern of -3, -2, -1. But when we're gaining electrons, well, that electron's going into the same part of the cloud as the others. They're all negative, so they're going to repel against each other. They're going to push away. And when they push away, that radius gets a little bit bigger. Well, if we gain 1, it's going to grow just a little. If we gain 2, it's going to grow even more. If we gain 3, still same energy level. We've got 3 extra electrons floating around in our cloud. That cloud's going to be larger. So that's how we get that overall trend of it decreasing across. Don't necessarily need to know the specifics, but if you ever look at the actual graph data, you'll notice it does get a little funky, a little bit wonky in bad misreadings, group 13, 14, 15. Now, ionic radius, when we're looking at comparing element to different elements, big picture works great. But what about if I'm comparing the ion to its neutral atom? Well, then you've got to think about what's going on within that cloud itself. So when we start having elements form bonds, they're going to gain or lose electrons to get an octet. They want an octet. An octet is 8 valence electrons. What's the magic number about 8 valence electrons? Well, that's the same as our noble gases. And that happens to be a full outer energy shell. So most elements want 8. So your metals will lose their valence and drop down to get their octet. Non-metals go out and they start gobbling up and they add electrons to get their octet. So when I'm comparing the atom to the neutral, or the ion to the neutral atom, I got to think about what's going on. Metals lose. So if a metal loses that electron to form that positive cation, I'm losing some things from my cloud. My cloud's going to get smaller. So think about it as like I got a circle of friends, and I lose some friends from my circle's going to get smaller. So when we form those positive cations, the metal ion is always smaller than its neutral atom. So specifically, let's pick on magnesium. So magnesium atom versus magnesium ion. Magnesium ion will always be smaller. That changes when you flip to your metals, your nonmetals. Non-metals always gain electrons. They gain those electrons to form a negative anion. As they are gaining their electrons to form that negative anion, their radius expands. I have a group of friends. I add more friends to my group. My group gets bigger. Same idea with the electrons. We've got our cloud. We're putting in a couple extra electrons. They're going to push and repel against the others that are already there. Therefore, the cloud is going to expand. It is going to get larger. So anytime we are comparing an anion to its neutral atom, the anion is always the larger of the two. So specifically, let's look at sulfur. If I was to compare elemental sulfur to sulfur ion, which is S-2, sulfur ion is going to have the larger radius because it has gained extra electrons. Therefore, the cloud is getting a little bit bigger. Alrighty, so knowing your numbers of valence electrons can help you predict the charges of your elements. We've revisited valence electrons. This is not a new concept. This is something hopefully you remember from physical science. If for some reason you don't, write it on your periodic table. Your valence electrons, remember, match the ones digit of the group number. So group 15 has 5 valence electrons. Well, in order to become stable, they want to act like noble gases. So if I treat the periodic table as like a cylinder, and I look at it and I put my group 1 really, really close to my group 18, notice that they're 1 away. They can have a noble gas configuration by losing an electron. When they lose that electron, they always form a +1 ion. Same thing. Same idea for groups 2 and 13. They always lose electrons to form positive ions. It is a pattern. Memorize the pattern. We will use this pattern throughout the rest of the year. You need to know the pattern. When you get to group 14 in physical science, you learn that 14 forms a positive or -4. Well, this is chemistry. So you want to start learning that the metals are going to be positive. We will see later where S and N get to do some SN and PB, tin and lead, do some funky stuff, and they don't always form 4s, but they're always positives. And my nonmetal, carbon, when it forms an ion, is always a -4 ion. My metalloids can kind of go either way, so we ignore them for first year chem. But nonmetals are negative, metals are positive. Now we are at group 15. Group 15. We got 2 choices. We could lose 5 to drop down. Or we can go out and we can steal 3. Because remember, our goal is to lose all of the valence or to gain to 8. And it's easier to go out and steal 3 electrons than it is to find a home for 5. So therefore, group 15 is going to form a -3. Pattern continues. Group 16 is a -2. Group 17 is a -1. Group 18, they tend to not form ions. The smaller noble gases do not react at all. Larger ones, though they can form bonds, they tend to not form an ion. They tend to form covalent bonds and share electrons to do some funkiness. But these elements in this nice pretty dark blue, they are your stable noble gases. And with the exception of helium, because helium is stable with 2, because our first energy level can only hold 2 electrons, all of the others have 8. That is that octet that you will hear us talking about throughout the rest of the course. Alrighty, last 2 trends, next to last, electronegativity. Mentioned that this is on your table, so you don't got to learn it. You just got to look at the table and remember that you can read the pattern from it. What is electronegativity? Well, electronegativity is the ability of an atom to attract electrons. So, nonmetals love to go out and gobble up and attract some electrons. Metals, not so much. They're wanting to push their electrons away. So metals have low electronegativity. Nonmetals have high electronegativity. So in general, and we can see on the periodic table where overall we have an increase as we go across. So specifically period 2, we go from a 1.0 electronegativity to a 4.0. Now, neon, argon, and helium have dashes, as well as your man-made elements. The reason neon, argon, and helium have dashes is because they do not attract electrons. They have no attraction to electrons. They don't want them. They got what they want. But everybody else, for the most part, has some type of an attraction. Either they hate them, they're a metal, or they love them, they're a non-metal. So as we go down, our electronegativity has a general decrease. It is harder for elements to attract electrons the bigger they get. So when we take those trends and we kind of look at them all together, fluorine is the most electronegative element on the periodic table. It has an electronegativity of 4.0. My least electronegative element, we don't consider the ones with the dashes because they don't count. My least electronegative is element 87, who's not on the screen. Again, that would be francium. So francium really, really doesn't want his electrons. He's giving them away like candy. Fluorine really, 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 really wants more electrons, like jonesing for that candy. Therefore, those two make the best of friends. So, last trend, last pattern. The last trend is ionization energy. Ionization energy is the energy needed to remove an electron. For our first chemistry class, we're only looking at first ionization energy, and it's just the energy needed to remove that first electron from that outer energy level. Well, thinking about what we already know that noble gases are stable, so they're not going to want to give up electrons. They're going to fight really, really hard. They're first going to have a very high ionization energy. Our nonmetals, they're stealing electrons, so they're not going to want to give them up. They're going to have fairly high ionization energies. My metals, on the other hand, they're giving the electrons away. It's going to be really easy to go up and steal one of their electrons. Therefore, they have low ionization energy. The general trend in first ionization energy is as we go across, we have a gradual increase in first ionization energy. But as we go down, we have a gradual decrease. It gets easier to remove electrons from larger atoms. Notice a lot of this connects back to the size. It is easier to remove electrons from francium with its 87 electrons. It's easier to go up and steal one of francium's electrons than it is to steal one of lithium's 3. Those 3 are pretty tightly bound to that nucleus with only 2 energy levels. But francium with 7 energy levels and 87 electrons to keep track of, that electron in that 7th energy level is just easy pickings. So there are a few exceptions. If you're looking at specific data, yes, there's some fluctuations, but trends is all about big picture. We can predict, looking at a placement on the table or looking at information that, hey, these halogens, group 17, are going to be really, really reactive. Group 1 are also very reactive, and that's because they're both 1 away from being stable. But my halogens, not going to want to give up those electrons, hence high ionization energy, high electronegativity because they really, really attract them. My metals, easy to get rid of electrons, so low ionization energy. They're giving away their electrons, therefore they have low electronegativity. Now, in terms of trends, this is a great little graphic. It has all of the trends summarized nice, neat, pretty, and together. Remember that on our periodic table, you can easily read atomic mass and nuclear charge. That general red arrow trend of increasing both directions is on the table. Not only can you read the red arrow, but on our periodic table, we've got this blue one here. The electronegativity trend of increasing across and decreasing down are both on our table. Therefore, if you just remember that electronegativity and ionization are really, really similar, your life is a lot easier. Last, but definitely not least, the other three trends tend to have the same overall pattern. You cannot read it explicitly on the table, but if you remember where your metals and your non-metals and your metalloids are, you can infer it from their placement and figure out that, oh, we increase down, we decrease across. Now, last but not least, of course, please, guys, make certain you're starting to memorize that pattern for charges as well as your valence electrons, which apparently are not on this graphic anymore. That is it for today. We will actually look at using these trends to put elements in order and using information about the trends to predict what element we are trying to identify. That is all for today. As always, remember, if you are needing any assistance with any of the chemistry content, please come to my open office hours or schedule a tutoring session with me sooner rather than later.